Smriti, can you see the slides?
Yes, sir.
And slides are changing now?
No, sir.
Only first slide you are able to see?
Yes, sir. Sir, not even full screen.
Okay, just. Okay, Smriti, we can start now.
Okay, sir. So I welcome all the participants to the last session of our 5 days ATAL FDP on textile design. For our last session, we have with us Professor Vinay Kumar Mita as our speaker for this last session. He will be delivering a topic on non-woven fabric design. So over to you, sir.
Thank you. Okay, now slides are visible, and you can see the changes also. No?
No, sir.
No, sir.
Slides.
The slides are not visible, sir. It is coming as blank.
Just. Now.
Period चालू है?
No, sir.
Not yet.
No, sir.
Yes, sir.
Let me rejoin. Okay, I'll exit and I'll rejoin. Yeah, can you see it now?
Yes, sir.
Yes,
No,
sir.
yes, sir. Now it is.
Yes, sir.
And slides are changing also?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Okay, good afternoon. So I'll discuss the non-woven textile design. As far as the production of fabrics are concerned, we can see these are the various options which are available with the production of the fabrics. We have the conventional structures, which are formed by the manipulation of the woven, knitted and braided structures in the form of woven, knitted and braided. Then we have the non-conventional ways of making the fabrics, which are made from the fibers directly with the help of the non-wovens, or we can do it with the help of the yarns and fabrics also. as for example tufted carpets. Then the fabrics with coatings are also available in the form of the monolithic or breathable structures are also possible. And as far as the nonwovens are concerned, these are considered as a sheet of the fibers or continuous filaments or the chopped yarns of any nature or origin, formed into a web by any means and bonded together by any means with the exception of weaving and knitting. So directly converting the fibers into the fabrics, that is the process which is done in case of the non-woven structures. We can use fibers also, even the cuttings of the yarns can also be used, continuous filaments can also be used, and they are basically converted into a web. And once the sheet of these particular fibers or chopped yarns is made, then we have to go for its bonding. And that bonding can also be carried out by various processes, which a few of them I'll be covering in this lecture. And there is an exception of the weaving or knitting process. So there is no need to go for the weaving or knitting. And you can also, they can also be considered as the non-woven fabrics consisting of the fiber mats, which are held together because of their inherent properties. Or by some mechanical process or chemical process involving the use of the chemical agents. So in some cases, we simply try to utilize the inherent characteristics of the fibers. With the help of that, the entanglements take place, or in certain cases, we can do it by mechanical processes or using some chemicals. Once the web is formed, then the bonding is carried out either chemically by mechanical processes or by simply using the inherent characteristics, frictional properties of the fibers. So in this particular slide, one particular simple diagram of the non-woven structure has been shown, which is being made with the help of the needle punching process. So what happens here is that with the help of the barb needle, which is shown in this particular slide, the barb needle is taking these particular fibers from the top layers to the middle and the bottom layers as it penetrates. The shape of the barb is such that it will take these particular fibers with it while going in the downward direction. But when these particular needles recede back in the upward direction, at that time, they leave these particular fibers at their new positions. Now, when this particular fiber is moving from the top to the bottom layer, for example, in this case, then it will be now taking this new configuration in the fibrous structure, web formation, which has been carried out over the layers in the form of the various laminar structure has been prepared. So it will be now moving from the top to the bottom layer. And during this particular process, it will get entangled between different layers. The fibers which are present in between different layers, it will get entangled with that. That is how the bonding is carried out. This is one way of doing the entanglements and getting the bonded structures. Others, for example, the chemical bonding, we discussed that some chemical will be used. With the help of that, the bonds will be created. And the other processes I'll be covering subsequently. So if we see nonwovens historically, the felts made from the wool or hair are the oldest fabrics which are made by the human being. And in earlier times, these felts were made from the animal hair using various chemical aids like water, urine, or the mechanical means of trampling and beating the fibers using the inherent frictional characteristics of the fibers. The felts were created. Either certain chemical aids like water and urine were used. And slowly, the other ways of forming the fabrics were invented by the human beings, by the formation of, for example, yarns that were invented, and with the help of those, the fabrics were being made. This is how the fabric formation actually started with the felt formation, and then slowly, with the invention of the yarn formation, we came to the formation of the woven and knitted structures. And they were found to be more useful than these particular felts which were being produced earlier with the help of these mechanical means or the chemical aids. And over these particular years, most of these particular woven and knitted structures have taken over the market of all the textile structures. In most of the textile applications, the woven and knitted structures were being used till around 20-30 years back. And this was the time when these particular non-woven structures actually again came into picture, and it was found that in certain applications now these particular materials are better than the woven and knitted structures. And because of these particular reasons, the utilization of these and the production of these non-woven structures is increasing day by day. And why these particular fabrics have again come into limelight, these are some of the reasons which I have listed here. First one is that this is a versatile process where there is no necessity that we require the fibers or even virgin fibers. So we can use any type of materials. As for example, in the first definition, I told that we can use even the chopped yarns. So the cuttings and waste of any type of textile materials can also be used in the production of the non-woven fabrics. Whether it is yarn or it is a fabric, any waste material, those particular materials which were regarded as the waste materials, they can be utilized in the production of the non-woven fabrics. So all these cuttings and waste of the yarns or fabrics, any type of fabrics, they can also be utilized in the formation of the non-woven fabrics. And so when waste is being used rather than the virgin fabrics, the cost of production of these particular fabrics is lower. In certain applications, we utilize these particular cuttings and waste. For example, in lower-end automobiles, you will find that car mats are being made from these type of waste or recycled materials. Then another reason is that the properties displayed by conventional textiles are in excess of the requirements. For example, in certain applications where the woven and knitted structures were being used, it was realized that in some of the cases, the properties which are actually required for that particular application, we are having these particular fabrics, these particular properties, and along with that, we have certain other properties which are actually not required. And those particular properties are displayed by the conventional materials of woven and knitted structures are excess of the requirements. For example, we want to go for thermal insulation. For example, I want to use a fabric for thermal insulation. So along with that, the woven and knitted structures will have many other type of properties which will be available with them. You have more strength of the fabric also. Elongation characteristics are also there, which may not be actually required. My application is only that I need a insulating pad, and it may not be having those particular requirements of these particular strength and other characteristics. So it was found that in certain applications, these particular properties are in excess of the requirements. So when we do not require these particular properties, then there is no idea of going into the manufacturing of the woven and knitted structures through that much of laborious process, which involves a lot of time and efforts, laborers. So in this particular case, this is another reason why the non-wovens have again come into picture. So for certain applications, we identified that these fabrics are much better than the woven and knitted. Then the third reason is that there is better utilization of the individual fiber properties than in the conventional textiles. So in certain cases, for example, I took the example of thermal insulation. So for thermal insulation, what we need is that we have to trap air inside the pockets are to be created in the structure so that more thermal insulation can be provided. And that we can do when the individual fibers can be utilized in making the structure. Whereas when we make the yarns, then at that time during twisting of the yarns, the inter-fiber spaces have been actually reduced. So it is the yarn formation which has taken place with the help of the twisting process, and because of that, the individual fiber properties are actually not being utilized completely. So in case of these type of applications, for example, thermal insulation or even for filtration also, what we need is that interfiber spaces are required to create these smaller pore size in the filters. So when I make a filter from the woven structure, for example, the yarn formation has taken place. So now the filtration will be taking place between the yarns. It will be the inter-yarn spaces which will be utilized for the filtration process. So for those particular these type of applications, inter-fiber properties will be playing better role as compared to the inter-yarn spaces. So it was found again that in certain applications, the individual fiber properties can be better utilized for the in the non-woven structures for certain applications. Then another reason was that we want to reduce the cost. So cost of manufacturing actually reduces because of various reasons. For example, the cuttings and waste are being utilized, and at the same time, the process has been shortened. We have reduced the process of making the fabrics. Yarn formation stages have been eliminated. So the process has been shortened, and we can produce the fabrics in a shorter period of time with lesser workers and investment. And at the same time, the speeds at which these particular machines actually operate, that they are very high. So in these particular cases, for example, wet laying process, which is quite similar to the paper manufacturing, the speeds almost equal to the paper manufacturing can be utilized in the manufacturing of the fabrics. Or in spun bonding case also, the speeds are very high. Hot air bonding, it is 5,000 times more than the automatic shutter. So because of all these particular reasons, the cost of manufacturing these particular fabrics is significantly lower than the woven and knitted structures. So because of these reasons, the non-woven structures have again come into the limelight. And in many of the applications now, you will find that the woven and knitted structures have been replaced by the non-woven structures. So because of these particular speeds, which I discussed in the previous slide, for example, all yarn preparation steps have been eliminated. For example, now to produce 5 lakh meters of woven sheeting, it requires 2 months of yarn preparation, 3 months of weaving process on 50 looms, and 1 month of finishing and inspection is required. Whereas the non-woven press process will be able to deliver the same quantity of the fabric in 2 months of time. So for those particular applications where we can use this particular process, it is always better to go for this particular process. And many of the applications, we are now shifting from woven to knitted, woven or knitted structures to non-woven structures. And the process is also automated, requires less laborers than most of the weaving and knitting processes. So it is also efficient in the use of energy. So for these reasons, the non-wovens have now again emerged into the big markets. So these are some of the definitions given by INDA and ADANA. These are the two organizations which are working for the development of the non-woven fabrics and their markets in Europe and America. INDA is working in America, USA, International Non-Woven and Disposable Associations, and ADANA is working in Europe, European Disposable and Non-Woven Association. So according to them, the definition, for example, ADANA's definition contains all the process actually of the non-woven fabric manufacturing, manufactured sheet, web or pad of directionally or random oriented fibers, bonded by friction and or cohesion and or adhesion, excluding the paper and the products like woven, knitted, tufted, and stitch bonded structures. So these are the standard definitions of the, and the now potential of the non-wovens is very high to replace all the flexible structures. As I have already discussed, that the production rates are very high and the cost of production is very low. And in certain applications, they perform better than the woven and knitted structures. So because of that, they are replacing most of the flexible structures containing the clothing, decorating, displaying, supporting, separating, filtration. In most of these cases, the non-wovens have replaced the woven and knitted structures. And they can provide innovative, cost-effective, and sometimes unexpected answers to innumerable business challenges. And the applications of the non-woven structures are ever increasing. These are some of the applications which I have shown here You have healthcare and hygiene sector, packaging sector, agriculture, upholstery, shoes and garments. In all these particular sectors, the non-woven structures have come. And if you see the market growth of these particular sectors, they are increasing remarkably. And they are expected to increase significantly, almost double than what we are having in 2018 or in these particular years, in the coming 5 years. So in the last 1996 to 2006, the average annual growth rate is 7.5% for these particular non-woven structures. And if you see non-woven growth by region, then China and the European countries, Mid East, these are the major countries where the growth is now taking place. Then if we see the per capita consumption, then this per capita consumption in Indian market is very low. In these particular countries, especially the Korea, Taiwan, Europe, America, in these particular countries, the non-woven consumption per capita is high, very high, which is very low in case of our, it is almost 0.1 kg in case of the Indian markets. This is again the same representation. India stands here. So there is a lot of scope for this particular non-woven structures, and huge quantities of these particular materials will be required in the coming days. And this is the projection of the consumption of the India and US per capita non-woven consumption from 2005 to 2050. So you can see this is the consumption, per capita consumption of Indian market, which stands at this moment at this particular point, and it is growing. And almost around 2050, you will find that it will be almost equal or closer to what the European American markets are consuming. This is how the growth of USA is, and the Indian markets growth is very high. And in the coming days, it will be increasing and will reach almost equal to the US markets in 2050. Then if we come to the manufacturing process of the nonwovens, then this is how the nonwoven fabrics are process involves: the web formation, then the web bonding process, then drying, curing, and finishing. So the complete dry laid process, wet laid process, and the polymer laid, these are the 3 different processes. We can do it from the staple fibers, and we can do it from the continuous filaments also. So for the staple fibers, we have these particular 2 routes, that is the dry laid process and the wet laid process. And from the filaments, continuous filaments, we have this polymer laid process, which involves the spun bonding and melt blowing process. Whereas in the dry laying process and the wet laying process, we have the wet formation taking place from the staple fibers. And then after that, we go to the bonding processes, which involves the chemical bonding, mechanical bonding, thermal bonding, and the solvent bonding processes. Now, when the web formation is actually taking place, at that time, we have various options available for the orientation of the fibres. We can have the different orientation in the form of parallel laid, cross laid, or the composite of these particular 2. And the random orientation can also be provided in these particular cases, which I'll be covering in the next slides. Then if we see the raw material which is being used, polyester is the most frequently used fiber in the non-woven structures in most of the markets, especially the United States. Then is polyolefins are also common in this particular non-woven markets for their strength. And cotton and rayon are also used for absorbency. Acrylic acetate, they are also being used in these particular non-woven structures. So this is how the orientation is, and this orientation of these particular fibers will be actually having effect on the properties of the structures. The strength and extension of these particular structures will depend upon the orientation, Then the bulk or fullness, that will also be dependent on what type of orientation has been given. And this is the first type that we call as the longitudinal orientation or parallel laying. So in this case, most of the fibers are now oriented in the direction of the fabric formation along the length of the fabric. Whereas in the transverse case, the fibers are oriented in the direction which is transverse to the length of the fabric. Along the width of the fabric, the fibers are now oriented. And in the combined, we have the longitudinal and transverse orientation, both can be carried out here. The properties of these particular structures of longitudinal oriented will be now more in the length direction. For example, the strength will be higher in the length direction because of the orientation of these particular fibers. And if we measure the strength of the fabric in the cross direction, the width-wise, then that strength will be very low. And this particular difference is around 5 to 7 times from the longitudinal direction, from the length side. And on the other side, if we go to the transverse orientation, then in that case, the orientation of these particular fibers is taking place along the width, but it is not exactly at 90 degrees to the length. It is at certain angle. For example, in this case, we can see 2 arrows. This is how the orientation is. For the continuous laying, certain angle is made, and at that angle, the laying of these particular sheets on this particular belt will be taking place. So you will go from top to bottom at this particular angle, and then you will come back up to the top, and the orientation of these particular fibers will be now preferably in the transverse direction. Not exactly, not completely in the transverse direction, but they will be more oriented towards the cross direction, towards the transverse direction. So in this particular case now, when the load is applied, so because of the orientation of the fibers, one component will be acting in the transverse direction, which is the major component, and the second smaller component will also be working in the longitudinal direction. So in this case, the strength of the fabric will be more in the transverse direction than the longitudinal direction. And this particular difference is not as high as in case of the longitudinal orientation. This may be only 2 to 3 times. The transverse direction strength will be only 2 to 3 times more than the longitudinal direction, which was more in case of the longitudinal orientation, because in this case, complete orientation is in the length direction. All the fibers, as they come from the carding machine, the web sheet is formed and they will be completely laying in the length direction. But in this case, because we have to do it in the transverse direction, so we do it at certain angle to maintain the continuity. And so the preferential orientation is in the transverse direction. A small component is still acting in the length direction. And in certain applications, for example, where I feel that the strength of the fabric should be almost equal in both the directions, it should not be like this, that it is 5 times less in the other direction, or this is having 2 to 3 times less in the other direction. So in certain applications, I may require that the strength of the fabric should be almost equal in both the directions. So for that reason, we go to the combined longitudinal and transverse orientation. While laying the fibrous sheet, half of the sheets can be laid in the longitudinal direction and rest half can be laid in the transverse direction, so that almost equal orientation in both the directions is obtained, and so the strength is almost equal in both directions. Then moving still further, sometimes I want that the strength should be equal in almost every direction, not only in the transverse direction or in the longitudinal direction, but at certain biased angle also. In any direction, the strength should be almost equal. So for that reason, we go for the random orientation. And this random orientation will be carried out, for example, with the help of the air currents. And with the help of that, the fibers will be now having no preferential orientation. They will be completely random in all directions. And because of that, when the load is applied, the strengths will be almost equal in all directions. So this is what we need to decide when the fabric is being designed for a particular application. for that particular application, we need to fix up that what will be the properties required, and accordingly, the orientation has to be decided. That what should be the orientation, whether I should go for the longitudinal orientation or I should go for the transverse orientation, or if I need almost equal strength in all directions, then I should go for the random orientation with the FIBRES. This is one small example how the longitudinal orientation will take place. The fibers will be laid on a conveyor belt along the length. So the fibers coming out from the carding machine have a preferential orientation in the machine direction. So they are laid in this particular way, and you get the longitudinal orientation. And these are other ways of making the longitudinal fabrics, and this is how the strength of these particular fabrics at different angles have been shown, right from 0 degree to 90 degree. The strength difference is huge. For example, at 90 degree, the strength is very low, and at this particular 180 degrees, the strength is high. So this is the significant difference which takes place in the longitudinal orientation. And when the transverse orientation I was talking, so this is how the transverse orientation at certain angle is carried. We take the delivery from the carding machine and lay them in this way at angle K, and then come back from this particular top side to the bottom in this way, and the overlapping will be carried. So this is how the transverse orientation of these particular fibers that will be carried. And this is the strength of these particular structures now, strength difference of these particular structures. In this case, again, there is difference, but it is not as high as in case of the longitudinal orientation. And when we go to the random orientation, where almost equal strength, I said that the orientation, there will be no preferential orientation. So in that case, this is how the angle-wise strength of this particular fabric will be. Almost equal strength in all the directions. So theoretically, it should be straight, but actual will be slight variation will be there, but there is no huge difference in any of the directions. And this particular random orientation is carried out with the help of these particular air currents. Opening of the fibers is carried out, and with the help of the air, now these particular fibers are laid on this particular conveyor belt. And when they are laid on this particular, falling on the conveyor belt with the help of the air currents, there is no preferential orientation of these particular fibers. This is another way of aerodynamic random. Another thing by which we can get this randomizing effect is in the carding machine itself. From the carding machine, the orientation of the fibers is in the machine direction. But in this case, we can put a randomizing or scrambling roller between the doffer and the cylinder. And before the fibers fall onto the doffer, the scrambling roller will take these particular fibers in the opposite direction. And because of this, the orientation of these preferential orientation of the fibers in the machine direction from here will get disturbed. And then when they are collected, they do not have the preferential orientation, which is normally observed in case of the carded webs. This is done in the carding itself by using the randomizing or scrambling roller. Otherwise, we have to do, if you are not using this particular randomizing technology by NSC, then you have to go for the aerodynamic web formation, which I have shown in the previous slide, for the random orientation. Then another, most of the nonwoven fabrics have one particular problem, you can say, that it is very difficult to control the GSM of these particular fabrics. Thickness and GSM variation in these particular fabrics is very high. And nowadays the technology has come which can monitor these particular GSM of the fabric on machine itself. And the control of this particular web weight can be carried out to maintain the uniformity. Then another orientation which is possible here is in case of random orientation, the structure is made directly by throwing these particular fibers onto the conveyor belt for the required GSM. For example, if 200 GSM is required, that 200 GSM may be obtained in case of the longitudinal orientation or the transverse orientation through a laminar process. That means layer by layer, we will be putting the layers of around 10 grams per square meter. Around 25 layers will be placed and you get to 50 grams per square meter of the GSM. So that is a laminar structure. Whereas when we do it with the help of the aerodynamic method, in that case, there is no laminar orientation, laminar structure. The fibers will be directly of around, if 250 GSM is required, the required fibers will be directly landing onto the conveyor belt without making any laminar structure. That is the difference between the longitudinal transverse oriented webs and the random oriented webs. And when the GSM of these particular webs is higher than 250 to 300 grams per square meter, then we can even find some of the fibers oriented in the third direction. Till now we have discussed that the orientation is taking place in either length direction or it is in the transverse direction. But if the GSM of the web is high, 250, more than 250, 300 GSM, then in that case, some of the fibers may be landing in the Z direction also, because all these particular fibers will be landing directly onto the conveyor belt without making a laminar structure. So some of the fibers may land in the Z direction.
लोग प्री बोर्ड्स को पहले कहाँ इतनी इंपॉर्टेंस देते थे, हमेशा बोर्ड्स को ही देते थे और हमेशा ये होता था प्री बोर्ड टफ होता था, बोर्ड
So when the fibers are directly landing in the same required GSM, the amount of fibers landing onto the conveyor belt is large. So some of the fibers may be landing in the Z direction, which is very useful when we are making the bulky structures or paddings. So they will have better compression as compared to the laminar structure of transverse and longitudinal oriented. So those fibers which are in the Z direction, they will resist this compression. So for these particular bulky structures or the beddings, we can go with the aerodynamic laying of the fibers. Then another method of orientation, giving orientation and changing the structural design of the fabric is that we can go with the perpendicular layering. Now in this case, all the fibers are, now you can see that this is the length direction. Then we have the width direction, and all these particular fibers are actually standing vertically in the Z direction. So in case of aerodynamic laying, I told that few fibers may be landing in the Z direction, which will resist the compression of the structure. But in this particular case, we are intentionally doing the layering of the fibers in the Z direction. No fiber is now in the X direction or Y direction. All the fibers are in the Z direction. So we have this type of machine, which is a wave maker or Syntex machine. So with the help of this, we have a conveyor belt and a wire grid. And in between the wire grid and the conveyor belt, we are pushing these particular carded web fibers, fibrous web, into the Z direction. And with the help of this reciprocating comb and the compressing bar, we are compressing these particular fibers vertically between the space created by the conveyor belt and the wire grid. So this is how the orientation of these particular fibers in the Z direction will take place. This is the Struto process or Syntex wave maker, which I discussed earlier. So with the help of this, now in this case, we have a forming disc rather than the reciprocating comb and the compressing bar. Here we have the forming disc. And with the help of this disc, these particular fibers are being pushed between these particular spaces to arrange them vertically. For example, you can see on the right side, these are the fibers, the pictures of these particular structures. The fibers are standing vertically. And once these particular orientation has been given, they have to be bonded right away so that these particular fibers do not lose their position. And once they have been bonded, then they will maintain this particular position in the structure. And this particular structure is now very useful for some applications where we require the compressional characteristics of the fabrics. This is another diagram of this particular type of the fabric. And the folds which are being created, they can be, the spacing between these folds can be changed, and we can change the other designs of the fabric. By increasing or decreasing these particular spaces, the structure can be changed. Fold frequency can be changed. Even the orientation of these particular folds can also be inclined. So with the help of the air bonding, in most of the cases, these particular fibers are to be bonded at this particular place only as soon as they are vertically arranged. So we use thermoplastic fibers in this particular case, and because of that, the air bonding is easily carried out. Polypropylene fibers are normally used, and they are bonded at a lower temperature, and easily the structure can be obtained. And if you see the properties, compare the properties of these particular structures, then you can see that this is the Stuto process fabric. The thickness of this particular fabric with respect to the application of the load and the compressional characteristics can be seen. So from here, when the load is applied up to 1200 pascals, then this length of the thickness of the fabric reduces up to this particular point. Whereas if we go with the air-laid spray bonded fabric, then it is here initially 15 millimeters and goes down to around 5 millimeters. So huge compression is taking place in this particular structure. Whereas this particular structure will be resisting the compressions, and this is the initial thickness, and you get the final thickness after this much of load, only this much is the difference. From 10 to around, you can say around 8. This is the 8 millimeters. And at the same time, if we see the compressional recovery, original percentage of the original thickness which has been recovered, then the polyurethane foam has also been compared. Number one is the polyurethane foam, which recovers almost around 97–98%. So this Stuto fabric, vertically laid fabric, is also very close to the polyurethane foam. So this is the area where this particular fabric is now being used. So you can replace the polyurethane foam with the Stuto vertically lapped nonwoven structures. In automobile industry, sound insulation for automobiles, depth filtration and air filtration, or even in thermal insulation. So in all these particular cases, we can use this particular structure for better performance. And as far as the automobile structure, which I was discussing, that you can have the foam, which is being used in the automobile complex. The three layers are there. One is the polyester fabric, the polyurethane foam in between, and you have the packing fabrics, polyamides. And in this case, now the polyurethane foam can be replaced with the help of this vertical lap structures to make the automotive complex. The polyurethane foam is applied here. The performance is the Stuto fabric is having almost equal performance, but the advantage here is that in case of the polyurethane foam, the process of putting this particular foam in between these two layers is very tedious, and it liberates toxic gases. And after the usage, even if you want to go for recycling the polyester polyamide fibers, even that is also not possible, because this particular polyurethane foam will remain adhered to the polyester fabrics, and they will not let you use this particular polyester fabrics for recycling. So it is better to replace it with the help of the polypropylene made Stuto vertical lap fabrics. Another method of layering the fabrics is wet laying process. Now, in case of the wet laying, as I told, that these particular speeds are almost equal to the paper making process, because this particular fabric formation has been invented by the paper makers. So from the paper maker making process, rather than using the pulp, the shorter fibers were utilized to make that particular product. And it was found that the product which has been made by these particular shortened fibers, that is having flexibility, flexible characteristics like the textile materials. So this particular type of process came into the market. So it produces these structures which are textile, having textile fabric characteristics, the flexibility and strengths, but the speeds are very much almost equal to the paper manufacturing. So very high speeds are there, and you get a fabric structure which is having textile-like feeling and characteristics. And in the total non-woven raw good industry, around 5 to 10% of non-wovens are made by this particular process. And if you know the tea bag which we normally use in our houses, that is made by this particular process. It looks like a paper, but it is not a paper. It is a fabric made by this particular process. हाँ जी कुलदीप जी. So this is how the wet laying process actually is done. The fibers are suspended in water, just like the pulp is used. In this case, very short fibers are used, and they are taken onto a perforated screen. The water will be filtered out, and the fibers will remain over the surface of the perforated screen where the sheet of these particular fibers is formed. That is what we say is the web formation, and then we go for the drying of these particular webs. Along with that, the bonding can also be carried out. For example, impregnation chemical bonding is used here for bonding this particular structure. The filtered water can be reused, pumped again, and it can be reused. These are some of the applications where the wet laid products, the coffee bags or tea bags, they are normally made from this particular structure. Otherwise, we have plug wrap papers, stencil papers, air filter papers, liquid filter papers, table linen, napkins, towels. All these particular products can be made from this particular wet laying process. Or if you want to go with the technical, then we have the glass fibers also added with this, and glass fiber roofing substrates are made. Glass fiber mats for flooring are made from this particular technique. Then even the latest technology is the application of these wet laid nonwovens is that Lenzings has offered flushable wipes. So these are the wipes which are made by wet laid nonwoven products, featuring a blend of the lyocell fibers and wood pulp. They have been now used by made by this particular technology, and this is 20% of the new lyocell fibers have been made, and 80% of wood pulp is used, and they will reach more than 90% of disintegration within 30 minutes when they are put in water. So this is how the non-woven fabrics can be used for different textile applications. Now coming to the bonding processes, these are the bonding processes. So these are the various mechanical bonding, chemical bonding, and thermal bonding processes which are used for bonding these particular fabrics. I think we can stop here. This is enough for today's lecture, and at 4 o'clock you have the test also.
Thank you, sir, for the wonderful presentation. Any question from the participants? Sir, I think there are no questions, even in the chat box.
Okay.
Thank you so much, sir.
Okay, thank you. टेस्ट के लिए स्मृति बोल दो सबको है at 4 o'clock they will be.
Okay, sir. Test will be conducted at 4 o'clock. So be present in this Microsoft Teams account. I'll share the link in the chat box.